Dear students, welcome to our second lecture and welcome to our exploration of probability laws. Probability began with games of chance, but in the recent time, it has become a fundamental tool in statistics that helps us to quantify uncertainty. The learning outcome in today's lecture are as follows. 1. We should be able to define probability from different points of view and perspective. 2. You should be able to understand and apply probability law to some real-life problems. And 3, you should be able to solve some practical probability problems. Going forward on this, there are 3 major views that we have as far as probability law is concerned. The first one is the classical view. In the classical view, we have n equally likely outcome, and n naught of these have attribute A. And for this, we say the probability of this event is given as n naught of divided by n. Or we say this equals to n of E divided by n, where n is the samples or the list of elements in the sample space, and n of E is the number or the list of elements in the event set. Having said this, the formula for computing probability under the classical view is given as probability of A equals to n naught divided by n. Now, for example, I can say that in a throw of die, for example, in a throw of die, what is the probability of a 2 coming up? The sample space here is a set of 1, 2, 3, 4, 5, 6. Okay? And for 2, let me say probability A is an event of event 2 coming up. So if A is the event of event 2 coming up, then A will be the set of 2. Then probability of A will be the number of A divided by n. Don't forget, I said the other time that n is the number of elements in the sample space, and n of A is the number of elements in the event set. Now, having said this, we have only 1 element in A and we have 6 in n. So this will be 1 over 6. Okay, so probability of A will be 1 over 6, which will be the probability of event 2 or outcome 2 occurring in a throw of a die. This is an example of what we refer to as the classical view of probability. The second one is the relative view. Okay, here, probability is the long-term relative frequency. Okay, we look at probability as a long-time relative frequency, and this is denoted as probability of E. Don't forget, E in this context is just referring to an event, any event, equals to n, the same n of E over n, but we take a limit as n tends to infinity. So what we are saying here is that we look at the probability of the number of the elements in event E divided by the total number of elements in the sample space, and we look at this as n tends to infinity, meaning that as this is repeated in a number of times. Okay, and this is what we refer to as the relative frequency view of the probability law. Having said that, we also have the last one that we call the axiomatic view. In the axiomatic view, it gives us 3 fundamental views or fundamental rules, which we call postulation. The first axiom here is denoted as probability of A is greater than or equals to 0. This is what we call the assumption of non-negativity. And this is how we get to know that probability values is a non-negative value. So your probability value cannot take on a negative value. Having said this, we move straight into axiom 2. Of course, for the assumption 2, we also say here that probability of S equals to 1. And here, S is actually seen as the sample space here, okay? And we call this a certain event or certainty. This denotes certainty. Now, I give you an example. If I throw a die, what is the probability that a figure between 1 and 6 will come up? Okay? If you say a figure between 1 and 6 will come up, that is a certain event. All right? Because n of S consists of 6 elements, and S itself consists of 6 elements. So this becomes n of S over n, which is 6 over 6. And that will give us 1. And that is why we say probability of S equals to 1, which depicts certainty. The third axiom, which I call axiom 3, is that probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. Okay? Now, we said this. This is what we call the additive rule. All right? But in a situation whereby we have what we call a mutually exclusive event. And what do we call a mutually exclusive event? It is an event where occurrence of one prevents the other from occurring. And I give you an example that if a coin is tossed, okay, if head occurs, it will prevent tail from occurring. This and other disjointed sets exhibits these characteristics. And for that, probability of A union B will be probability of A plus probability of B. Because for a mutually exclusive event, the intersection will not hold because one has prevented the other from occurring. And in a disjointed set, okay, there is no intersection. All right. So probability of having the intersection between A and B will be 0 at that point. And this can be better depicted by using a Venn diagram where we have event A, we have event B. This is event A, this is event B. So if I ask what is the intersection between these, okay, you can see that there is no intersection. All right. But in the proper sense of it, probability of A union B is actually telling us something like this, A, B. And the interest that we have here, if we have to shade the area where we have probability of A union B, it will be all this area except that of the intersection. And this intersection here is where we call A intersection B. But for the example that I gave, or for the scenario that I painted, if the intersection is impossible, or if the event A and B are mutually exclusive, it means that the intersection or the probability of intersection is an empty set. And in that state, probability of A union B will simply be probability of A plus probability of B. Having said that, let's look at some example. He said, let's solve this one. What is the probability of getting at least 2 heads when tossing 3 fair coin? Probability of getting at least 2 heads. So here, the interest is at least 2 heads means probability of S less or equals to 2, where S here is the number of head, okay, in a throw of 3 coin. For any good student, the first thing to do is to first of all identify the sample space. Now, for 2 coin, we have head, tail, head, tail. I'm doing this so that it won't be difficult for you to be able to compute the sample space. Having done this, then I have head, tail, head, tail, head, tail, head, then tail, tail, then tail, head, and tail. Now, the sample space is what we have here. 1, 2, 3, 4, 5, 6, 7, 8. 8 observations. Okay, having said that, then our interest is less or equals to 2, because the example is at least 2 heads when tossing a fair coin. All right. Now, when we say a fair coin, it's a coin that is not loaded. And if we are tossing a coin that is a fair coin, we expect that the probability of a head coming on and a tail coming on is both half, 1/2. Okay, that's the definition of a fair coin. All right. So here, looking at events where head is less or equals to 2. So it means that we have here where we have 2 heads, we have here where we have 2 heads. So these are the scenarios where we have at least 2 heads. So our probability, okay, of x less or equals to 2 will then be the number of x over n, which is the sample space, and this will be 4 divided by 8, and this will be 1/2. So the probability of x less or equals to 2 is half. So thank you for your attention. Now, what we have succeeded in doing today is that we have introduced ourselves to the concept of probability law, where we have viewed probability law in 3 different forms. One, looking at it from the classical point of view, from the relative frequency point of view, and from the axiomatic point of view. And on the classical point of view, we are able to say that the number of elements in the event we are considering divided by the total number of elements in the sample space would naturally give us the probability of the event we are interested in. Okay, taking the limit of this structure is what gives us the relative frequency approach. And in the axiomatic approach, this is where we also talked about the 3 axioms or propositions or probability that are very, very important to the understanding of probability concept. One, we said that probability of A is greater or equals to 0. This is a non-negativity assumption that tells you that probability values cannot be negative. The second axiom tells us that the probability of S is always 1, which is certainty, which denotes certainty, meaning that when you look at the probability of elements of the sample space, this will naturally be equal to 1. And the third one is the additive rule of probability, where we look at the probability of A union B to be probability of A plus probability of B, especially when A and B are mutually exclusive. And we also introduced the concept of mutual exclusive event or mutually exclusive event, where we said a occurrence of one prevents the other, or when we have disjointed sets. In these 2 scenarios, the intersection is always an empty set, and then it does not fit into the additive rule of probability. Thank you.